So just like there is linear momentum in translational motion, there is angular momentum in rotational motion, in which this is denoted as vector L, and the definition of this is R cross P. Just like how torque was defined as R cross F, and this equals to I alpha, angular momentum L is defined as I omega, and this is parallel to how linear momentum P is defined as mv, and inertia is the rotational analog of mass, and angular velocity is the rotational analog of velocity. Now, when force was equal to 0, then momentum was conserved. Similarly, when torque is equal to 0, that means angular momentum is conserved. Conversely speaking, change in momentum equals to the integral from t initial to t final of f dt, and change in angular momentum equals to the integral of t initial to t final of torque with respect to time. Now, this conservation of angular momentum is really useful in planetary motion, because in planetary motion, the major force is force of gravity, and this force of gravity is parallel with r. What I mean by that is, if there are two masses, m1 and m2, then the force of gravity, they are directed towards each other, which means if I set the r-axis, then the force of gravity is parallel to the r-axis, therefore the torque from the force of gravity equals to r cross fg, which is r times fg times sine theta. But since theta equals 0, this sine theta term becomes 0. Therefore, angular momentum is always conserved. So for example, let's say there is the sun with mass ms, and there is the earth mass m, and we're assuming that the mass of the sun is far greater than mass of the earth, so the sun just stays stationary. If they're separated by a distance r0 and the earth is moving at a speed v0, let's say later on this motion at the opposite half of this trajectory, the earth is separated by a distance 1/2 r0, then if I want to calculate the velocity of the earth, then since angular momentum is conserved, r cross p in this case equals to r0 times mv0 should equal to 1/2 r0 times m times v. Therefore, v should equal to therefore 1/2 v0 equals to v, therefore v equals to 2v0. Now, if I want to get specific value of v, then I can use conservation of energy to do so. 1/2 mv0 squared minus gmms over r0 should equal to 2 mv0 squared minus 2 gmm over r0, where on the left hand side is the total energy of the earth at this position, and the right hand side is the total energy of the earth at this position. Canceling out the mass of the earth and moving this term to the right and moving that term to the left, I get gms over r0 equals to 3/2 v0 squared, and therefore I get v0 equals to square root of 2 gms over 3 r0. So a physicist named Kepler came up with 3 laws about planetary motion, and the first one is that the planet's orbit is an ellipsis, and the sun's position is one of the foci of the ellipsis. So if this is the position of the sun, then the planet would go around the sun as the equation of an ellipsis. And the position of the sun would be one of these 2 foci of this ellipsis. Now, this has been mathematically true because the force of gravity, which equals to negative gmms over r squared, is inversely proportional to r squared. But if force of gravity has different law that was not inversely proportional to r squared, then Kepler's first law of planetary motion would not hold true. The second law is that if the planet goes around the sun, let's say that's the sun, with the polar function of r of theta. Then the area swept by this planet, let's say for the time interval t1, the planet has swept an area a1, and for time interval t2, this planet has swept an area a2. Then a1 equals to a2 if the time interval t1 and t2 are the same. This is true because remember in polar functions, the area equals to the integral of 1/2 r squared d theta. And from chain rule, this equals to 1/2 r squared d theta dt from t initial to t final. Now note that this equals to omega, or the angular velocity, and also the angular momentum, which equals to I omega, is in the form of mr squared omega. So therefore, the area, which equals to 1/2 r squared omega dt, is equal to integral of 1/2 m times L dt, in which within the bounds of time, this equals to 1/2 m times L times delta t. Therefore, this proves that area swept by the planet is proportional to the time interval. So therefore, as long as the time interval is the same, the area swept by the planet is equal. The third law states that the square of the period is proportional to the cube of the semi-major axes. And the semi-major axis of the ellipsis is the longest distance from the center of the ellipsis to the edge of the ellipsis. Now, in circular motion, the force of gravity equals to the centripetal force, which means gms over r squared equals to mv squared over r. And solving for v, I get v equals the square root of gms over r. So therefore, t, which equals to 2 pi r over v, equals to 2 pi r times square root of r over gms. And therefore, this is proportional to square root of r cubed. Therefore, from circular motion, we see that t squared is proportional to r cubed. And similarly for ellipses, Kepler stated that t squared is proportional to the cube of the semi-major axes. Now I've prepared several questions regarding angular momentum and rotational motions from the recent F equals MA exam. And the first one's from year 2016, question 8. This question is about Kepler's law of planetary motion, in which previously I've claimed that the second law, in which the line containing the sun and the planet sweeps out an equal area in equal time, this is a consequence of angular momentum conservation. However, for the first and the third law, this is a consequence of force of gravity being proportional to inverse square of r. So therefore, only 2 would be true because the second law is the only law that is independent from the force law. The next one is question 17 from the same year. In this question, there is a ping pong ball traveling at speed v and rotating at angular velocity omega. And there is a friction force that is opposing the velocity, in which after this friction force has been applied, the ping pong ball is at rest, which means both the translational velocity and the angular velocity is 0. So therefore, the impulse caused by this friction force equals to negative force of friction times delta t, in this case equal to negative mv. And change in angular momentum would be negative torque, in which in this case equal to force of friction times r times delta t, which equals to negative I omega. And since ping pong ball is a hollow sphere, inertia equals to 2/3 mr squared omega. Canceling out the r, I get negative friction force. I get negative friction times time as equal to negative 2/3 of mr omega. And since these two equations have the same term here, the right-hand terms must be the same. Therefore, negative mv equals to negative 2/3 mr omega. And canceling out the m and the negative sign, I get v equals to 2/3 of r omega. Now, in this question, we've shown that v is not necessarily r omega, and this is because the ping pong ball isn't rolling from the surface, but instead it is slipping, and that is why v equals r omega does not hold true. So the next question is from 2017 F equals ma, and it is a series of questions from question 11 to 12. In this problem, there is a rod of length L and mass of 2m. And at the edge, there is an object with mass m. If a mass with mass big M is approaching the system at speed v0 that is perpendicular to the rod and at height h, the question is asking at what h would this system after the collision would not rotate. Angular momentum equals to I omega, in which if the angular momentum equals to 0, then omega would be 0, and therefore this system would not be spinning at all. Now remember, in the beginning I've defined the angular momentum as r cross p, and this r here is with respect to center of mass. This is r center of mass. What I mean by that is, let's see if that is the center of mass of the system. Then if the momentum of this mass is parallel to the distance, or r center of mass, then the cross product of r cross p, which equals to r times p times sine theta, would equal to 0, because theta, the angle between r and p, is going to be 0. And in order for that to happen, h is going to be x center of mass of this mass rod system. And remember, previously I claimed that the x center of mass equal to the sum of m and its respective position divided by the total mass. And if I set the coordinate system as of x as the upward direction, such that the position of this m is 0, then the center of mass would be 2m times L over 2, because L over 2 is the center of mass of this mass of the rod alone, plus m times 0, because the position of the mass is equal to 0. And this is divided by 3m, because 3m is the total mass of this system. Crossing out the m, I get center of mass as L over 3. So therefore, if h equals to 3, then that means r is parallel to momentum, which means L is 0, as well as omega equals to 0. So therefore, on the answer choice, B would be the correct answer. So the next question is continuation from question 11, in which what is the relation of big M as a function of small m? But note that my whole logic behind solving question 11 was based on what would be the condition such that the angular momentum is going to be 0. And that condition is that momentum should be parallel to displacement with respect to the center of mass. And that means the mass of this object, or big M, does not matter. So therefore, for question 12, any mass, big M, will work. So question 25 from year 2017 F equals MA. This is, based on my personal experience, is one of the hardest questions. And before talking about this question, I would like to talk about the characteristic of an ellipsis. In an ellipsis, there are 2 points called the foci, which are located in the semi-major axes like this. And one characteristic of an ellipsis is that the distance from the 2 foci to any point in the ellipsis, so if this is D1, D2, and that is D3 and D4, then D1 plus D2 equals to D3 plus D4. And this value equals to 2 times the semi-major axis. So therefore, in this question, if this distance is 0.5a, then the other foci is also located at 0.5a from the edge. And this distance here, this distance combined with that distance must equal to 2a. If I call this distance x, then this distance must equal to 2a minus x. And since this is perpendicular along the same major axis, the Pythagorean theorems holds true, so therefore 2a minus x squared must equal to x squared plus a squared, which means 4a squared minus 4ax plus x squared equals to x squared plus a squared. Canceling off the x squared and dividing each side by a, I get 4a minus 4x equal to a, so therefore x equal to 3/4 of an a. Note that angular momentum equals to r cross p, which is r times mv times sine of theta. And in this case for v1, theta isn't pi over 2, so therefore angular momentum at v1 isn't x times m times v1. Instead, I'm going to make a new variable, position 3, where the velocity equals v3 and the location is exact opposite to the location of v2. Now in this case, v2 is perpendicular to r. So therefore I can use conservation of angular momentum between v2 and v3. So therefore m times 0.5a times v3 equals to m times 1.5a, because distance from here to here is a and distance to here is 0.5a, and times v3. These two quantities are the same. Canceling off the m and the a, I get, sorry, here should be v2. I get v3 equals to 1/3 of v2. Then, using the law of conservation of energy, I get 1/2 mv2 squared minus gm big M over 0.5a equals to 1/2 mv3 squared minus gm big M over 1.5a. And plugging in the value of v3 into here, I get 1/18 mv2 squared minus gm big M over 1.5a. And if I move this term to the left and that term to the right, I get 1/2 minus 1/18 mv2 squared equals to 1/0.5 minus 1/1.5 gm big M over a. And the left hand side, this becomes 18/8 mv2 squared equals to 2 minus 2/3 gm big M over a, which is 4/3 gm big M over a. Therefore, gm big M over a equals to 18/8 times mv2 squared times 3/4, which becomes 1/3 mv2 squared. Now from here, since I got gmm over a as a function of m and v2 squared, I can express potential energies as a function of v2. So therefore, using conservation of energy between v1 and v2, I get 1/2 mv1 squared plus gm big M over 3/4a equals, sorry, there should be a minus sign, equals 1/2 mv2 squared minus gm big M over 0.5a. And plugging in the value of gm big M over a, I get 1/2 mv1 squared minus 4/3 times 1/3 mv2 squared equals to 1/2 mv2 squared minus 2 times 1/3 of mv2 squared. And moving this to the right hand side, I get 1/2 mv1 squared as equal to 1/2 minus 2/3 plus 4/9 of mv2 squared, in which this becomes 5/18 mv2 squared. Therefore, solving for v1, I get v1 equals to square root of 5/3 v2, and therefore v2 equals to 3 over square root of 5 of v1. Now, this problem seems very mathematical and very complicated, but this problem is based off of two fundamental ideas of physics, which was conservation of angular momentum and conservation of energy. And since conservation of angular momentum wasn't that convenient for v1, I've made a new variable called v3, in which conservation of angular momentum can be readily used, in which whenever you encounter such problems like this, I encourage you to actually expand a variable, expand multiple variable in fact, such that the equation of motion will be readily solved. Now, final question is from your 2018 A, F equals ma, question 21. In this problem, there is a ping pong ball where this is not spinning, and the ping pong ball is traveling at the speed v naught. Then, after some time has passed, and due to force of friction, the ping pong ball is rotating at speed omega and traveling at speed v prime. And since this ping pong ball is rolling without slipping, v prime equals to r omega. Then the question is asking, what is the time for the ping pong ball to take from the initial condition to the final condition of rolling? Then the impulse applied by the force of friction equals to negative force of friction times delta t, where delta t is the time interval. In this case, this equals to m v prime minus v initial, since this is the final momentum minus the initial momentum. Change in angular momentum, since this led to increase in angular momentum, this is positive r times force of friction, which this term equals to torque, times delta t, which is I omega. And since ping pong ball is a hollow sphere, this equals to 2/3 mr squared omega. Canceling off the r term, I get force of friction times delta t as 2/3 mr omega, which from this relation equals to m v naught minus v prime. Since r omega equals v prime, I get 2/3 mv prime equals to mv naught minus mv prime. And therefore, solving for v prime, I get v prime equals to 3/5 v naught. Then the time it took for the ping pong ball equals to change in velocity divided by the acceleration, in which acceleration in this case equals to force of friction divided by the mass. Now, since there were no other external forces, I can safely assume that there's going to be force of gravity, and there's going to be the normal force, which equals to mg, and the force of friction is going to be mu Fn. In this case, it would be mu mg. Therefore, the acceleration, which equals the force of friction divided by mass, is simply mu g. Therefore, time, which is v naught minus v prime over force of friction divided by mass, equals to v naught minus 3/5 v naught over mu g, which is 2/5 times v naught over mu g. And looking at the answer choice